Welcome to my Research Express. In this video, you will learn about data fitting. Linear fit. Let's start by considering some sample data. We have two arrays x and y, representing the independent and dependent variables, respectively. In MATLAB, we use the polyfit function to perform linear data fitting. We need to specify the degree of the polynomial fit, which is 1 for linear fitting. The coefficients variable now holds the slope and intercept of the fitted line. We can use the polyval function to generate the fitted line using the coefficients obtained from the polyfit function. Let's visualize the original data points along with the fitted line. Polynomial fit. MATLAB comes with the census data inside, which contains U.S. population data for the years 1790 through 1990. Let's load it into MATLAB by typing this. Within your workspace, you now have two newly introduced variables, seed_date and pop. The seed_date variable is a column vector consisting of years ranging from 1790 to 1990, increment by 10. On the other hand, the pop variable is also a column vector, containing the corresponding U.S. population figures for each year specified in seed_date. Let's do the simple plot by typing this. As we can see, this census data does not spread linearly but tends to spread exponentially and even polynomially. For a polynomial fit of the fourth order, we can type this. The warning occurs due to the polyfit function utilizing seed_date values as the basis for a matrix with significantly large entries. The wide range of seed_date values leads to issues with scaling. To address this, one possible solution is to normalize the seed_date data. So, let's do this. Here, we normalize seed_date by centering it at 0 mean and scaling it to the unit standard deviation. An alternative approach to normalizing the data involves leveraging prior knowledge of the solution and units. For instance, in this dataset, setting 1790 as the reference year, or year 0, would have yielded equally satisfactory outcomes. Now try the fourth-degree polynomial model using the normalized data, assess the polynomial's performance at the normalized year values and create a graphical representation by plotting the fit alongside the observed data points. The fourth-degree polynomial model equation has the following forms, so, according to this result, our fourth-degree polynomial model equation becomes. The problem now is that we do not know whether our data fitting was good enough or not. One way to quantify the quality of the fit is by examining the residual, which represents the disparity between the observed and predicted data points. The closer the residual value is to 0, the better the data fitting. To give you a clearer picture, let's apply the fourth-degree polynomial fit model and the one-degree polynomial fit model and see which one is the best for our data above. Let's plot the fourth-degree polynomial fit model and its residual at the top and the one-degree polynomial fit model and its residual at the bottom. As you can see, the fourth-degree polynomial fit model is better than the one-degree polynomial fit model for our census data because it has lower residual values or is more spread around the value 0. The error bounds. Error bounds play a crucial role in assessing the adequacy of your data's fit. These bounds can be obtained by using the polyfit function's optional second output parameter as an input parameter for polyval. In this example, the polyfit and polyval functions are employed to calculate error bounds for a fourth-order polynomial model. Again, we normalize year values by the previous method. This code uses an interval of 2 delta, corresponding to a 95% confidence interval. Exponential fit. Let's say you measure a quantity y at various times t. The plot suggests that a polynomial function could be able to model the data. Consider the following two-degree polynomial fit model. You may calculate the unknown coefficients a0, a1, and a2 by typing this. The solution is found with the \# operator. Therefore, the second-order polynomial model equations are as follows. Now evaluate the model at regularly spaced points and overlay the original data in a plot. It is obvious that this fit does not accurately approximate the data. We could either increase the order of the polynomial fit or explore some other functional form to get a better approximation. Instead of using a polynomial function, we can explore a function that works well with linear changes in its parts. For instance, the exponential function could be a suitable option in such cases. Again, the unknown coefficients a0, a1, and a2 can be calculated by typing this. According to these values, the fitted model of the data is. Now, assess the model by computing its values at evenly spaced intervals and then superimpose the initial data onto the same plot. This is a much better fit than the second-order polynomial function that we have applied before. That's all for this video. For a more comprehensive explanation and step-by-step guide, please go to the link in the description. If you find this video useful and helpful, please support me by clicking the like and subscribe buttons. Don't forget to ring the bell so you don't miss the other learning videos from my Research Express, your gateway to data analysis mastery. Thank you for watching.